Okay, so let's have Anand Natarajan from MIT tell us about some confessions.
Okay. Yes, the title of this talk is the quantum games PCP results and confessions. So just this overview of the talk. I'll tell you what this quantum games PCP conjecture is and why people formulated it and what's kind of known about it. And then also I will confess to an error in a result that I claimed with Thomas Vidick in 2018, which was a claimed resolution of one version of this conjecture. And I'll explain the mistake that we made, and maybe the mistake suggests some interesting open problems, or maybe the open problems are trivial. I guess you guys can decide. So, okay, so let's jump into it. So, what is the classical PCP theorem? So, we all know kind of the version that we usually quote is in terms of constraint satisfaction problems, right? So it's I'd say it is n. Are we in ADS space? Is there a reflecting boundary? So given a 3-sat formula B, it's NP hard to decide if max sat of phi is, let's say, equal to 1, or at most 7/8 plus epsilon, right? So max sat just means the maximum fraction of the clauses that you can satisfy. So this is the thing that we usually generalize when we talk about the quantum PCP conjecture, right? So I guess the very top of this board is okay still? Okay, anyway, you all know the conjecture, so it's okay. Right, so we kind of just translate. So what is the quantum version of a 3-sat formula? Well, we kind of think the right answer is a local Hamiltonian. That's the quantum version of a local constraint satisfaction problem. So, given local Hamiltonian, we want it to be QMA hard, I'll call it H, to decide. And just to stick with the max, theme over here, I'll say lambda max, although people usually talk about the minimum eigenvalue. It's totally equivalent, of course. We're going to decide if it's greater than or equal to some A or less than or equal to B, where the difference between A and B is a constant. And also, we need to kind of make sure we understand the normalization here. It's here, the scaling was set by the number of clauses, right? So this is the fraction of clauses that you can satisfy, and that goes from 0 to 1. So here, I guess the scaling is set by the operator norm of H. So we want H to have operator norm at most 1. So then this difference is kind of a constant fraction of the total amount of energy you could have according to H. So this is reasonable. I mean, certainly this statement implies that this problem is NP hard, right? Because you can just take the Hamiltonian that corresponds to the SAT formula. So that's what we usually think about. And I guess there's also versions of this in terms of probabilistic checking of proofs. Harry and co-authors have this nice paper really spelling out these equivalences and giving nice reductions between them that came out very recently. So this seems like a natural question. Unfortunately, as you heard this morning, we have very little positive progress towards this. The best we have is the NLTS kind of Hamiltonians. I guess there's multiple constructions now, but they're all constructions of error-correcting code Hamiltonians. So they have no computational hardness in them. They're just structurally interesting results, but we don't have any sort of partial progress towards showing QMA hardness for this problem, I would say. Okay, one might ask, okay, maybe we should take some inspiration from how this theorem was proved in the classical world, right? So how did people prove this? They didn't, by my understanding of the history, they didn't start out by just attacking the hardness of approximation of SAT head on. They actually sort of, there was this work on multiprover interactive proofs, and the ideas from there are eventually got translated into showing this result. So a totally equivalent statement you could write in the classical world is, if I write lower down on this board, is that okay for everyone? Okay. So We can call this like the games PCP theorem, which is that, so this is going to introduce some jargon. So there is an MIP proof system for NP, for any language in NP, we might as well take 3SAT, with the questions. So it's a 2-prover, 1 round MIP proof system for NP with questions sent to the provers of size log of n and answers returned by the prover that are size O of 1. So what is an MIP proof system? If you're not familiar, the setup is basically you have a polytime verifier, you have these 2 all-powerful provers. In this case, there's 2 because I said 2-prover. It's 1 round, so the verifier sends each of them a question, and then they each send back an answer. And then the verifier applies some polytime computation to determine whether to accept or reject. So here, I guess I'm saying that there's an MIP proof system for 3SAT, which is extremely succinct. So like if this Q was like, if this A was like O of n, then this would be trivial, right? Because you wouldn't even need the 2 provers. One of them could just give you the whole assignment to the formula, and then you could check it. But here, yeah, there's something where the questions are like really short, and the answers are really short, and it's still NP hard. It still encodes this NP problem. So these things are kind of. Oh yeah, I guess the verifier is polytime. Yeah.
Like polytime or polygon?
It's polytime. It has to read the whole formula to start with. Yeah. So.
But then, like when you
things are encoded.
Okay.
Oh, I see.
I guess like for that, this is the reason why I don't see why it's equivalent, because like polytime, when you blow it back up by an exponential, becomes exponential time.
Oh, I guess we're not going to blow this up by an exponential. So what is the equivalence, I guess, is, so if you have this statement, why does this statement follow? It's by this transformation called the clause variable game. So essentially, you can construct a very simple MIP, which is like, I just ask prover 1 for a clause in phi, and I ask prover 2 for a variable in that clause. And they're supposed, like, this guy's supposed to respond to me with the values of the 3 bits that are in that clause, and this guy's supposed to respond to me with a single bit. And then I just check that they're consistent and that clause was satisfied. So it turns out that you can show that, like, if you had this gap here, like between 1 and 7/8, then you get here like a gap between a success probability of 1 and a probability of like some constant bounded away from 1. Well, I guess I should also say, that's a good point. I should say the completeness and soundness here are like, let's say completeness equals 1 and soundness is a constant away from 1. So does that direction at least seem reasonable? Okay. And the other direction is kind of, if you have this statement, then, okay, I guess to get exactly SAT is a little bit more complicated, but to get some sort of local constraint system, you can take this proof system and just imagine the, okay, so I guess the other direction is a little bit more complicated because you have to think about the verifier, but morally it's like, think of a description of the strategy of the provers in this interaction. Like that thing is just a table with, for every pair of questions, it has the answers that they would give. And this table is of size like 2 to the q times a. So, a strategy, a classical strategy is a table of size 2 to the q times a, right? Because like for each, or 2 to the 2q, I should say, it's like for each pair of questions, you write down what answers they'll give, maybe times 2a. So this is a polynomial size thing, because q is log n. And then to simulate the verifier in this proof system, you kind of just, the verifier was going to send some questions that corresponds to just reading some pair of entries in this table. And then you're checking that those entries satisfy some condition, which is some sort of local constraint. So you're doing some kind of local constraint on like 2 positions in this table, and that's like a 2 local CSP. And then I guess you can translate that to SAT. Yeah. Yeah, that's right. Right. So it's easy to translate it to SAT by just some simple gadget, I guess. Okay, so that's why these 2 things are equivalent classically. And I guess like historically, like people actually showed like a scaled up version of this. Like they showed MIP equals NEXP. So like non-deterministic exponential time has MIPs with poly-size communication, and then with a lot of hard work, you can like scale everything down by a log factor to get this result.
In this case, you don't care about how complicated provers.
That's right. Yeah. Although it's like true that in this case, like the provers are actually, given the answer, like the assignment to the SAT formula, they can compute their answers in poly time. That's actually, I'm going to come back to that point. That's a good question to ask. Any other questions at this point? Okay. So so motivated by this, I think actually. Maybe even at this very, this very institute, Vidick and so I don't actually know who first stated it in print, but I'll just say Fitzsimmons and Vidick in around 2014 proposed that maybe we should look at a quantum version of this to get some insight towards the QPCP conjecture. And so they proposed like what I call a games QPCP conjecture. And so the most bare bones statement you might ask here is like kind of an exact analog. So you would say there is an MIP star proof system. So I'll define that in a second, but it's like the quantum version of MIP. Okay, we want to talk about QMA ultimately, so let's put QMA where we saw NP with Q equal to O of log N and A being O1. Right, where MIP star is like you have entangled provers. And it's also like, let's say 2 prover 1 round, but any number of provers, any reasonable number of rounds would be interesting. Right? Okay, so that's the conjecture. Any questions about this statement of the conjecture?
Why is this the natural thing and not some MIP where I can exchange qubits?
Oh, okay. You could also ask that. I guess this is a stronger thing to ask for than where you exchange qubits. Yeah, that's actually, I think, so their paper in 2014 actually gave a protocol where you exchange qubits, and it achieved like, I guess these parameters, but the completeness soundness gap was inverse poly. It was not constant. So that was like interpreted by them as like evidence towards this.
There are also sometimes reductions. Like if you can send messages with qubits, you can convert that to a protocol where you just exchange classical bits.
Yeah, like you kind of delegate everything to like one more prover.
Yeah. I see. Yeah. So MIP stars in some sense includes this thing that you said.
Yeah, although those reductions are not so great for the soundness gap, so I don't. In this case, we do actually want it to be constant. So you might not want to use a black box reduction for that. Yeah.
Basically, remind me some point. So is Q the length of proof? I mean, I just want to ask the definition of Q and A.
Oh, great. So Q is the number of bits in the question sent by the verifier, and A is the number of bits in the answer. So it's the length of the questions and the length of the answers.
So the verifier is quantum here in this case?
It's classical. The verifier is still classical. Only the provers are quantum. Anyone else?
Yeah. Just to check, MIP star equals RE is when Q and A are holy, right?
That's right. I'm glad you asked that. Okay, so Yeah, so this is the perfect segue to, okay, so the next part, I guess this talk is going to be, I have like good news for you about this conjecture, and then I have bad news. So I'll start with the good news, which is, as some of us, as we may have heard, we actually know what this class MIP star is equal to in the general case where Q and A are poly-size. So we know that it's equal to RE. So it's like, all recursively enumerable languages are in this class. So you might ask, does that like automatically give you this result? So let me just write. So we know that MIP star, Q equals poly, A equals poly, is equal to RE. So this doesn't automatically give you this, right? Because here I really want the question and answer size to be small, and here they're like big. But it turns out that you can take the techniques from MIP star equals RE and like push them a little bit further. So this is something that in joint work with Tina Zhang we did. So NZ23. So okay, what is the idea? The way this MIP star equals RE thing works is like there's kind of a tool called compression, which says like given an MIP star protocol, I can generate a new protocol that has exponentially smaller questions and answers, but still decides the same language. And so you might think, okay, what if you can get to poly, why not just like keep compressing further and like get it even smaller? And this miraculously seems to work, at least to some limit. So we showed that RE is actually equal to MIP star with Q constant and A polylog of n. And I think, okay, I don't think we actually wrote this down here, but I think it should be achievable with current techniques to get polylog n and A01 as well if you want. Maybe using some variants on like the answer reduction PCP composition stuff in here. But because this is like the headline result we had there. So yes, that's like, okay, so this seems kind of incomparable to that. This seems kind of close to what we want to get here, except there's an annoying polylog. Because QMA is obviously contained in RE, so you have an MIP star protocol for QMA.
Randomness is constant, then isn't the soundness gap constant by definition?
Oh, not necessarily, because like the provers answers are not deterministic in the MIP star setting. Right, so like you could have protocols where like they generate the right answers, with probability like very close to 1, but not exactly 1.
So hold on, if you have this Q equals polylog and A equals O1, why is there like some padding argument to get you to log in? So like if you pad RE, it's still RE.
That's true. I hadn't actually thought much about that. Okay, maybe we should talk about this offline. Okay. I feel somewhat skeptical, but okay, I'll tell you at least why we.
That won't help you for Q&A.
Yeah, I guess so. The first question is, will it help you with QMA? Yeah, I guess we should talk about this offline. I'm not 100%. Maybe it'll work. I can say why we got the polylog here. Like the polylog here comes from this comes from kind of this analysis of the. It's like if you take so this uses like a lot of classical PCP machinery, including the low degree test, which is like central to like all the classical PCPs, and kind of the best quantum analysis we have of this low degree test has a worse dependence than the classical analysis. So that's why you get a polylog instead of a log, where you get it with like the classical construction. So I guess maybe there's like a padding thing we missed, but it seemed like you would need to actually improve this analysis to do better than polylog here. But I'm not.
I
count on that.
Padding, like,
Yeah.
what this really says is that you have a protocol for the halting problem.
Yeah.
And if you pad it, you're just going to get a protocol for the padded halting problem.
Yeah.
I think.
I think what's going on here is that this analogy between the quantum PCP conjecture and the games version happened before MIP star equal to RE.
Yes. Yes.
Whereas after MIP star equal to RE, you want to restate the games version to say, is there an MIP star proof system with QMA provers?
Exactly. Yes. So I'm about to get to that. Yes, that's exactly right. Yeah. Yeah. Okay, but before I get there, let me just like say one more remark about this because I think it's kind of neat. So like, you might ask, why did you stop at polylog or log, as the case might be? Like, why can't you get like log, right? Like, why can't you get any smaller? So it turns out you can show by some kind of essentially counting arguments that like log is the best you can do. So so I guess you can show that any MIP star for, I guess, actually doubly exponential time, so in particular for RE, requires Q plus A. If the total question plus answer length is at least, I think we even have an actual constant. It's like a half Q plus A is at least log n or something. And this just comes from some like explicit circuit lower bound, which I guess comes from diagonalization. Like kind of if you had a protocol with extremely short questions and answers, then like some sort of table describing the optimal strategy might be like advice that would let you solve the problem. And like there's lower bounds on how much advice you need to solve problems. Okay, but now as Umesh pointed out, like this conjecture, so this is, good news, like the complexity class inclusion is true up to polylog factors-ish. But this doesn't seem to say anything interesting about the original quantum PCP conjecture for Hamiltonians because it's involving like reducing QMA to RE. And now you might say, oh, maybe I can open the box and like see what do the honest provers actually do in this protocol when I'm trying to solve a QMA instance. But what they do is not very nice. It's like you have to first reduce QMA to some classical non-deterministic time class, so like n time of exp of n, nx, and then compute like the Cook-Levin tableau of like a Turing machine for this n time class, and then do some quantum stuff on top of that to like prove facts about this Cook-Levin tableau. So this is really saying nothing interesting about Hamiltonians at this point. Yeah, so I guess this suggests that maybe the modification we should make is so we want kind of this, and the honest provers should be, I guess, quantum polynomial time given copies of a QMA witness So this in particular means they're allowed to do things like in MIP star, like the provers share entanglement. That's like the source of their power. So when they set up their entangled state, they're allowed to use copies of this QMA witness to prepare this entangled state. That seems fair.
So do you expect with that modification, games quantum PCP would imply QPCP like this?
Good. So I still don't think there's an implication. Like it's certainly this argument that we made here in the classical case completely breaks down, right? There's no notion of taking a strategy for provers, even efficient provers in this protocol, and converting it into a quantum state that you're reading, local chunks of. Because here, even though the honest provers are QPT, like they could be measuring, they could have some state that they prepared from psi, but then in response to a question from the prover, they could be measuring all the qubits and then doing some complicated processing of the outcome to get their answer. And you can't simultaneously write down all their answers in like a big table, right? Because they're quantum.
Can you not also say limit the amount of shared entanglement?
You could do that. You could limit it to like poly n qubits or something of shared entanglement. I mean, that's like actually inherent. That's like true here by this definition because I said that they're QPT and like the only resource they get is like, I guess, poly many copies of psi. So they just can't create states that are bigger than polynomial.
How about if I don't limit the computational power, but I limit the...
So could you repeat the question?
The question is if you don't limit the computational power, but just limit the shared entanglement, I think then you can execute the protocol from here. Like then you can, because kind of computing this like huge Cook-Levin tableau is like, that's like all classical. So you can do it without the shared entanglement. And then you only need the shared entanglement to like sample indices into the tableau. So you only need like logarithmic in the size of the tableau amount of entanglement, which is polynomial. So yeah, so I guess that, yeah, our goal is kind of to rule out this, right? So and force like the protocol to be more interesting. Any more questions? Okay, so this is the question. This is the conjecture you might ask. And now, okay, so now comes for the confession part. So let me erase this.
Sorry, did you see the result part of the results in confessions yet?
Oh, the result part was just this, like the RE is like it might be start with like open questions and polynomial answers.
But the work with Tina was the flipped.
Oh no, that was also the work with Tina. So the flipped
Okay,
one is not
yeah.
written down, but I think we can obtain it easily from what we
Okay,
have. Yeah.
so you're referring to that work with Tina. Okay.
That's right. So that's the result. Yeah.
Okay.
Okay. There's at least one result. Let's talk. Okay. So the confession is so in 2018, Thomas Vidick and I had a protocol that we claimed had solved exactly this, except not with 2 provers, but with 7 provers. It was a 7-prover one-round proof system with, I guess, basically these parameters. I mean, so there's another subtlety here in that so this paper depended on an earlier result analyzing the quantum soundness of the low degree test, which also turned out to have a bug in it. But that paper at least has been fixed except for like a polylog lost in the parameters. So if you use the like fix to that paper and plugged it into our thing, what you would have claimed is there exists an MIP star with 7 provers, 7 efficient provers in the sense that I have on the other board for the local Hamiltonian problem, like the standard QMA complete version of local Hamiltonian with Q equal to polylog n, and I think we were able to get A down to 1. Yeah, A to 1. Yeah. So unfortunately, a portion of this, so this protocol had like several parts. One of the parts is actually like still used in the MIP star equals RE protocol. That part, is fine, but there was a part dealing with transforming the Hamiltonian to make it amenable to checking on the provers. And that part is broken. So, so this is, not known to be true. So, so I guess in the remainder of the time I have, which is I guess 15 minutes, I will tell you kind of what the bug is, and then maybe it suggests some interesting questions. So, okay, so how does this protocol work? Structure of the protocol. So we have these like 7 provers, right? P1 up to P7. Talk to the verifier. So the way we set it up is that they share a state amongst themselves, which is like some encoded version of a state that you get by just copies of the ground state to your original Hamiltonian. So for now, it's not super important how this encoding is done. It's like done with an error correcting code, but so they shared the state, and then we have a tool that's like called the, confusing enough, the quantum low degree test. But it like basically lets you force the provers to measure tensor products of Pauli's. And in fact, only Pauli X and Z in this paper on their share.
Any sequence of tensor product. It can
Yeah.
be n-qubit tensor product.
Any n-qubit tensor product. It can be a non-local tensor product. But you just tell them the tensor product to measure, and they measure it. So this is the part that's like still used in the MIP star equals RE protocol. So this I'm just going to assume is perfect from now on. Like if you tell them to measure, you know, a particular Pauli, they will do it for sure. They'll be honest in that. And so the question is basically, if you have this power of like forcing the provers to measure these non-local Paulis, how do you actually use that to check that, you know, the answer to the local Hamiltonian problem, where, you know, naively, like you want in the end to have a constant completeness soundness gap here, but the local Hamiltonian problem, the version that's QMA hard, has an inverse Pauli gap. So you have to amplify this gap somehow and exploit the property that you have non-locality in the measurements you can do.
So is the tensor product of Pauli's really crucial, or could you have like other products, global operators, even if
Like other tensor products of operators?
Yeah.
I think the Paulis, so they have to be operators that you can test with the non-local game. So I think probably for any single qubit operator, you can probably devise a non-local game to test it. Like at least I now know how to do X, Z, and Y. I mean, people knew how to do it for a long time, but I now know it. But I think like kind of there are tricks in the non-local games literature to get single qubit operators. But so yeah, maybe like any tensor product of like single qubit operators from like some finite set is local. Yeah. Like single qubit binary observables, I should say. Binary observables, yeah. Yeah. So kind of what we claimed is this. So we are given, you know, Hamiltonian H such that like this is the usual setting of the local Hamiltonian problem. So the operator norm of H was at most 1. And you know, in the yes case, so let's work with like maximization again to be consistent. In the yes case, lambda max of H is greater than or equal to A. And in the no case, lambda max of H is less than or equal to B, where A minus B is like 1 over polygon. Right? What we want is we want to create some H prime such that, okay, so let me write down something which will be not entirely correct. This is kind of where the subtlety arises, such that lambda max of H is greater than or equal to A prime, lambda max H prime less than or equal to B prime, where A prime minus B prime is O1. And the input object was local, right? So each term only acted on constant number of qubits. But this thing, there's no requirement that it be local. The requirement is instead that this is like a sum over some Paulis from some set S with like some coefficients maybe. So it's like, it can be decomposed as tensor products of Paulis. This has to be poly-size. There's actually like, we actually had a construction with an exponential size set and then did like a randomized reduction to subsample from it. So that's kind of doable in general with like a matrix turn-off bound. So that's not a barrier.
But for that, you need the betas to the norm of beta to sum to 1.
Exactly. Okay. So this is the issue. So this is like, I kind of fooled you by writing operator norm of H prime here. This is like not actually the right condition you want. So to understand why, let's think about what happens in this protocol, right? So in this protocol, all I have the power to do is to measure a Pauli of my choice, right? So what's the natural thing you would do is you would take a term in the Hamiltonian. Is it okay if I erase the conjecture? Okay. So yeah, I guess like energy. Like what's a natural energy estimation procedure is like pick an I in S with probability of I kind of proportional to beta I or its absolute value, and then measure P sub I, and then to get a bit B, which is let's say 0 or 1, and then accept if B is equal to like the sign of beta I, right? So if beta I is like positive, then and you get like +1, then that means you're like aligned, so you have like a high energy, so that's good. You should accept, and if you get a 0, that means you're not aligned, and you should reject. So like you can check that like the acceptance probability of this thing is like proportional to the energy, maybe like the bias away from a half or something. But unfortunately, okay, so to make this make sense, you need to like have this probability of picking the ith Pauli be proportional. It should sum up to a valid probability. So you have to normalize everything by the sum of the absolute values of the beta i's here, right? So really what you get is like, you get like the probability of acceptance. I think it's like a half. Okay, don't quote me on the half, but it's like a half times, the average value of the energy divided by the sum on I absolute value of beta I. So I'm going to call this quantity here the Pauli 1 norm of H. So it's just like the 1 norm of H when you write it in the Pauli basis. So this is actually the scaling that's relevant for this particular protocol, right? Not the operator norm of H. And so you actually need this. And yeah, and this is the thing that we don't know how to do. So except 3 minutes, I'll tell you like what we actually did to amplify. I'll take like 1 minute, and then
Sorry,
yeah.
just to get some information. So
Yeah.
if the beta is all equal,
Yes.
Equal in magnitude,
Yeah.
that would still cause a problem?
That would still cause a problem, yeah.
Yeah, so
That's
can
right.
you walk me through it? So what's the...
Yeah, so the issue is, okay, so maybe here's some intuition. So if I have a local Hamiltonian, if H is local, say it's K local, I claim that the Pauli 1 norm of H is always like related by constant factor to the operator norm. Okay, maybe I should write it the other way, but it's related a constant factor to the number of terms. Right, if I have a local Hamiltonian, because like each term just corresponds to a constant number of Pauli coefficients, and each coefficient is bounded like between 1 and -1. So this is like, this condition is kind of like the same as the operator norm, because the operator norm generally scales as the number of terms for these Hamiltonians. So this condition for local Hamiltonians is the same as the operator norm being bounded. But for non-local Hamiltonians, this is very false. So just take like the example of the Hadamard matrix, which unfortunately is also denoted by the letter H. So yeah, so take x plus z over √2, right? So this thing has operator norm equal to 1, right? Because it's a binary observable. and it has a Pauli 1 norm equal to like 1 over root 2 plus 1 over root 2, which is root 2, right? So then if you take like this thing tensor powered k times, for instance, like the operator norm remains 1, but the Pauli 1 norm, it also is like multiplicative under tensor power, and it becomes root 2 to the k, which is exponentially big. And here, this is an example where all the coefficients are of equal magnitude, like they're all 1 over root 2 to the k. But there's 2 to the k. I guess it's related to the problem. Yeah, yeah.
The commute, then you don't have any problems. The commuting ones add up in the norm, sort of in a spectral norm way. It's the ones that anti-commute.
Oh, yeah, exactly.
Too slow. You always get these factors of 2 then.
Yeah, that's exactly right. Yeah, because like non-commutation is what causes these two norms to be separated. Yeah. So, okay, now that I've given this example, now I'll tell you what the amplification construction we did is. It's basically this. So like our amplification was just like taking h. So first you like shift it so it's positive. So it's, you can do like I plus h over 2. So this is, originally this had operator norm 1, so it was between 1 and minus 1. Now it says positive. And now you can just look at like this thing raised to a polynomially high tensor power. And this is like good for the eigenvalues kind of because, if you have 1 over 1 minus poly n and you raise it to a poly n, then that becomes like a constant away from 1. So yeah, so that was the amplification procedure we did, but just you can construct simple examples where by this phenomenon, like the Pauli norm blows up under tensor amplification. So okay, so then I'll close with kind of like the open question. Like the open question is really, so I pointed out that like for, let me say it this way. So the first question is this. So we know that to get the full quantum PCP, it suffices to have like a locality preserving amplification, right? Like you take a local Hamiltonian, you turn it into a new local Hamiltonian with a bigger gap. And we saw that like this condition that the Pauli norm like should be bounded is like this, in the local case, it's like identical to the operator norm being bounded, right? But in the non-local case, like these things could be different. So like a weakening of this is that, is precisely the, can we get an amplification where the Pauli norm is sort of bounded? So is there an amplification to a non-local Hamiltonian where the gap over the Pauli norm is constant. So this should be strictly easier than that, but I guess I don't know how to do this. But maybe this is like and maybe the Pauli norm is not the only thing you can consider here. Maybe there are other weakenings. Yeah. Promise gap, yeah.
Sorry, well, Pauli 1 norm would be like polynomial in the number of qubits, right?
Oh, that's true. It can be polynomial number of qubits. I guess the thing is like here, for this, you want promise gap over operator norm to be omega of 1. And the operator norm and the Pauli 1 norm in the local case are always related by a constant. Well, actually, I guess they're not obviously related by a constant, but
It's low degree and low degree.
Yeah,
Yeah, you need a little bit more than just locality.
that's true. Because you don't want like some
Not too
cancellation.
many anti-commuting operators, basically.
Yeah.
If you have indeed low degree would work. Yeah.
Okay, so I guess local plus low degree.
Yeah.
I guess it still suffices, and then it actually makes this statement true. Okay, thanks.
Sorry, what is degree?
I guess it is not like all.
The amount of terms of one qubit talks.
I think that's what we mean here.
Sparsity. Yeah, sparsity. Yes, that's a good word if you're already using degree for something else.
Oh yeah.
Is it true for SIK model where the norm is
No,
and
it's not sparse.
but it's not loading is like. Oh,
No, like there's like a single fermion talks to everyone, right? In the SIK model.
Right.
And you can do a sparse SIK model, but this is genuinely different behavior.
I see. Quick question. So, does your construction say that quantum PCP implies MCC?
I think it.
Is the soundness preserved?
I think so. Yeah, because if you have a local Hamiltonian, then I think you
Right.
just decompose on the Pauli basis and sound is
It's already- okay.
Yeah, that's right. Well, up to like log versus polylog.
Okay.
Okay, just to conclude here, like I guess, or like other weakenings of locality that I don't know, like maybe these are interesting. I guess like a second question, just kind of like maybe this setting of like where the Pauli one norm is like not that much bigger than the operator norm. Like maybe this is kind of somehow similar to the theory of like max K Lin with imperfect completeness. I mean, so this is kind of I kind of just like thought of this this morning, but I guess the point I'm trying to make is that like if you have a system of Paulis that's like this is like Paulis are kind of like the quantum analog of linear equations, right? And so this setting where like the Pauli norm is like only slightly bigger than the operator norm, that's like somehow corresponding to like only moderately frustrated system of quantum linear constraints. And like we know that classically these things are already like NP hard, right? Like when you want them to be perfectly unfrustrated, like that's in P because of Gaussian elimination, but when you allow for like a constant amount of frustration, then it's NP hard. So I don't quite understand like the complexity of like this class of Hamiltonians. Like maybe there's some reason that they're already contained in NP because they behave like the classical case.
Not enough commutation.
Yeah.
Too much commutation.
Too much commutation. Yeah, like everything either commutes or anti-commutes. So maybe there's some algorithm that can like solve these. So I guess that's it for my talk, and thanks for listening.
We have time, so we'll move on to the next one. But while the student is setting up, we can ask questions.